All right, so today is a part 2 of this Heterotic mini-series, and the third quarter of the installment will be done by Muyang Liu, and it will be on geometry of heterotic ALE instantonic little string theories. What a title. Take it away.
Sorry, too long maybe. Good afternoon, everyone. Thank you for giving me the opportunity to start as the second half of our mini series in the Quiver Meeting. So today I'm going to introduce, and I should say focus on the geometric counterpart of the heterotic ALE instantonic little string theories. So this work is based on a trilogy of our published and upcoming papers with a collaboration with Michaela and Paul, who is in the audience. And as I highlight here, I will focus on the second part of the trilogy work, namely to study the geometric counterpart. And we also have anticipate another following up project with Andreas Bruns as mathematicians, which will explore more possibilities from the underlying geometry. Okay, so let me first start to motivate a little bit. Then one may be wondering why we need geometric engineering, especially using F-series techniques to study and construct the 60 little string series. So that refers to, first we should recall the ultimate goal of our trilogy work is to determine novel heterotic ALE instantonic series that extending the previous result in the literature as I listed here. And we noticed that those little string series has a universal two-group structures that talks about the mixed strings of the symmetry from different dimensions. And we hope to study those two-group structures and using the matching criteria obtained from the group structure to identify the T-dual partners among the novel little string series we found. Let me give a quick recap of the results from the previous talk, or maybe the first part of our trilogy work, namely that we have determined many novel little string series that governs the heterotic E8 cross E8 ALE instantons. They depend on the choice of connections mu1 and mu2 at infinity. And in the previous talk, we utilized the dual brain picture in the type 1 primes to explore T-duality and identify the T-dual partners for the ALE spaces of the type A and D. But however, for ALE spaces of type E singularities, the perturbative string series description is lacking. So that inspires us to instead seek approaches using F-series techniques. Namely, we studied the geometric counterparts of the 61,0 little string series as a liquid fiber carbonyl threefold. And then this allows us to explore the non-perturbative regions of the superstrings, namely the type 2B, easily. And due to the advantage of the geometric constructions in F-series, so first one can easily interpret the 60 little string series which packs a lot of information into a quiver by the geometric configuration, naming those curve configurations, those intersection patterns in the F-series geometry. And moreover, the T-dualities are realized as inequivalent vibration structures of the same geometry. So in our trilogy work, we use mainly two directions to construct the geometry relevant to the little string series in 60 dimensions. First, we employ the toric constructions that have utilized the combinatoric data from the toric geometries. And the second, we can also explore the little string series from the non-geometric heterotic backgrounds, especially that we focus on some certain types of the extreme trimal K3 surface that gives us many novel types of the multi-T-dual families. And as the main purpose of my talk is to give the introductions of the geometric counterpart, I will just show an appetizers of the novel little string series derived from the toric constructions that I will advertise to the talk later to present many interesting applications about finding results that's relevant to exotic differential family. That includes interesting phenomena like the discrete holonomies, the non-geometric heterotic background, and also to refer to the third paper of our trilogy work, namely we investigate the geometric engineering limit of pure heterotic strings in ARE spaces. And moreover, thanks to the M-series F-series duality, one can probe the 5D modular space, which is much larger than the 6D little string series in F-series after a circle reduction. And at the end of the day, thanks to the concrete geometric structures, one can confirm the predictions of the T-dual partner we proposed in the first part of the trilogy work, and also the talk that Michaela mentioned last week. In this section, I wish to briefly review the basic geometry concept relevant to the heterotic little string series. So expertise with experience about before about constructing either SCFT or little string series using F-series geometry can feel maybe safely to skip certain part of it, which then jumps to the more interesting part when I talk about case degenerations or maybe the Rose-Noble heterotic string series in the later section. And here I want to start to review F-series briefly in a nutshell. So right now, above in the headings, I listed many good review papers about F-series. So readers, for readers that wish to study more details of F-series, please refer to those references as I listed here. So the main idea of the F-series is to identify the axion diviton tau in the type 2B series, which controls the string couplings to the complex structural modulus of the torus fiber T2 over the base, such that the F-series string communication is given by those T2 vibrations of the base Bn-1 that the total overall vibration space is a Calabi-Yau fiber space Yn. And the more interesting physical phenomena happens once the torus fiber, or sometimes elliptic fiber, becomes singular over discriminant locus sigma inside the base. That I depict very brief visualizations of the movement when you move the torus fibers that varies over the base. That namely over a generic point of the base, the fiber is smooth. Once you move to a special locus of the discriminant components, the fiber becomes singular. And we will heavily use the toric constructions to get the equivalent resolutions of the singular later. And in the dual brane pictures in type 2B, the D7 branes are located at the components sigma I of the discriminant. So these overall techniques allows us to consistently engineer configurations with non-local PQ7 branes, easily use the vibration data. Okay, then I moved to the constructions of the 6D string series. By easily dimension calculation, then we realize we need an elliptic fiber Calabi-Yau threefold, which is given by the vibration I expressed here. And the base of the vibration B2 is non-compact. This is very nice that it reflects the fact that our little string series, similar as SFT, is decoupled from the gravity. And so far, there is the two types of the base topologies of the 6D string series up to birational equivalence deformations. Here I listed. In particular, we focus on the first type of the base because they are those bases due to the heterotic little string series. And moreover, the information from the base B2 that gives you different degrees of freedoms once you move to the discriminant locus. Namely, the compact one will yield the gauge degrees of the freedoms, and the non-compact one supports the favor symmetries. At the end of the day, our ultimate goal is to interpret all the relevant data of the little string series quivered by the geometric ingredients. So let's first interpret the little strings. In 6D, we noticed that the non-critical strings arising from these three branes were wrapping compact curves, that the string charge lattice is interpreted easily by the integral holonomy lattice of the second cohomology groups of the base B2 with its pairing. And this pairing that gives, after certain choices of the bases, Wi gives naturally the intersection forms as eta ij. And this eta ij, denoted as a matrix, gives very important information of the relevant little string series. Namely, the rank of this pairing gives the number of independent dynamical tensor multiplies. And also this matrix exists a unique no eigenvector required by the little string series. Namely, the eigenvector is sigma 0. And once you use these three branes to wrap this compact curve sigma 0, it will render to a so-called little strings, which has finite string tensions in everywhere in the modular space. And now, given the key ingredients, namely the little strings in the 6D series, one can compact the relevant data of the little string series into the following types of the generalized quiver, such that each notations will have the relevant interpretations using the geometry concept, but which is also translated to the D7 branes information as I listed here. So we have the gauge algebra, denoted by the 7 branes wrapping a curve that given Wi and Wi with self-intersections eta Ni. And once the neighboring curve has a non-vanishing intersection numbers, we interpret that those two neighboring gauge nodes can form to a bifundamental matter. And we use the square bracket GFI to denote the non-compact favor brane algebra GFI that intersect the adjacent curve. And those Ni refers to hypermultiplies that not originate from obvious brane intersections that is not easily, we can see that in the geometry correspondingly. And moreover, the fibration can also admit a very interesting non-trivial section structure, which will generate an abelian groups. So in the later talk of Paul's second half, that he will interpret the explorations of the geometric models with those non-trivial global structures. Namely, we use the torsion part of the modular groups to give rise to the non-simply connected symmetry. They are acting diagonally as on the center or subcenters of the favor symmetry as well as gauge shift symmetry that renders the total symmetries as this form of the quotient. The next step, after I talk about the geometrization of the 6D string series, we hope to interpret the T-dualities. So this will be easily handled that once you notice that the Calabi threefold X may admit multiple inequivalent vibrations structures as I denoted by pi and pi tilde here. And the KK theory corresponding to the circle reductions of the 6D series is given by the M series on X, such that one can probe the M series modular space of X larger than the F series modular space. And once you have a different 6D uplift to another F series, this is to say that we geometric realize the T-dualities between those two 6D series. Given the interpretations of the T-dualities in the geometry, I hope to review or recap a little bit about the matching criteria we proposed to identify T-dual partners. this is coming from the so-called continuous two-group symmetries that is existed in the all little string series, namely that we mix the one-form symmetry U1 to the various types of zero-form symmetry, such that we require that the two T-duality string series must have the matching following criteria. The first category comes from the two-group structure constant relevant to the Poincare symmetry, the asymmetry, as well as the Fourier symmetry. And rows eta ij and ii are the relevant data appeared in the 6 quiver. And the HGIV is a dual Cox vector numbers of the relevant gauge algebra GI. And also we require that they must have matching column branch dimensions and amounts of the Wilson line parameters. So I want to emphasize that the KR that usually gives us the most constraining and non-trivial restrictions. But however, KP has nicely interpretations in the Horowitz pictures. Namely, it counts the number of the neighborings. So since we only have two possible birational inequivalent based topologies, KP can only take two values, namely 2 and 0. In our talk, we'll focus on the first type. So given the interpretations of the geometry relevant to a 6-digit string series, I wish to continue to interpret the constructions of the heterotic AOE instantons in the F-series geometry. So namely, we noticed that in the Horowitz picture.
I have a question.
Oh, yeah, sure.
In the previous topic, you had formulas for Coulomb branch properties. And you don't have any formulas for Higgs branch properties?
So of course we can talk about the Higgs things between different string series, but I don't think that they are like preserved once you through the Higgsing process. So right now we care about those preserving data once we move around the T-dual network.
So you choose not to talk about the Higgs branch?
So because I have very limited experience about Higgsing, so I refer my colleagues' talk in the second half of this mini series today to talk about the Higgs branch. Right?
The formulas are geometric, just like those formulas, no?
Yeah, I know.
Yes, I see. So it's not a good idea to talk about both Higgs branch and Coulomb branch.
So I think
definitely, I think that I agree with the comment of Paul in the chat. No, the Higgs branch has to match as well. The dimension of the Higgs branch must match. Yes,
indeed. Yeah.
Oh, you have not looked at it. I see.
No.
Oh, I see.
It's a good question. In the end, it's
You
exactly the very same geometry. So that should also agree. Yeah. The sort of the number of complex structures, if you wish, they should also agree it's the same geometry. Yeah.
Yeah, should be similar formulas, right? I mean, yeah. Okay. Thanks.
The question is whether using the Higgs branch you can compute the higher group structure constants. That's another. And that
you are cut.
So matching of the should be a criterion that one can use. Oh, yeah, apologies. I have a very bad connection today.
I see. So you're saying for other computations, the Higgs branch will not be will not shed further light, or is this what you said? We lost Michele.
There's a comment in the chat.
Yeah, there's a comment in the chat.
The question whether one can use the Higgs branch to extract two-group structure constants is open.
I see.
I just as a quick comment, I tend to agree to with Michele. I would say that similar with the dimension of the Coulomb branch, is usually not enough information to really fully extract, say, the two-group structure. One thing we know for sure is that the two-group, the kappa p that Muyang wrote, that one is always greater or equal than the dimension of the Coulomb branch. But apart from this, the dimension of the Coulomb branch alone is not typically enough data to sort of bootstrap. The only thing we know is that the two-group must be greater or equal as a numerical value. But I don't think it would be really enough data to completely bootstrap it. But would be interesting to look at for sure.
Okay, thank you.
Thank you. Why is it not? Okay, it's moving. Okay, so I need to speak up, and let me quickly review this.
Don't worry about speeding up. You can take your time.
No, Paul has a limit on the chain catch up.
Yeah, I think it will be fine.
Okay, he will be fine, hopefully. So thanks to the horizontal pictures, we can realize the heterotic instantons in terms of the n fibrins is it's parallel to the two M9 branes, and in type 2b, such 9 fibrins emerges as C2 mod Zn singularities, which means that in F theory we can geometrically engineer those n copies of heterotic E8 cross E8 instantons in terms of realizing as a C2 mod Zn singularity at locus of the 2-1 curves intersect at the degenerating limit of K3. So I'll have more slides later to the descriptions of K3 fibrations. This is to just briefly review how we introduce the alien instantons in the geometric setups. Okay. And in our work, we heavily use the toric constructions. The reason is that one can easily obtain the resolved, equivalently resolved Calabi-Yau threefold from the combinatoric data from the relevant polytopes data. So first, we aim to construct a non-compact Calabi-Yau threefold with this data, that polytope. First, we construct the smooth toric ambient space alpha from the fan where the fine star and the triangulations of the rays that forms the delta. This gives you a smooth toric ambient space. Has the following fibration structures, which is given by the 2D toric surface, the weak final surface over the base B2. And once you cut the anticanonical surface inside the ambient space, this gives you a Calabi-Yau threefold. And this construction is perhaps one has the advantage that the liquid vibrations on X is inherited from the vibration structures in the toric ambient space naturally. And of course, the base B2 here is coincident with the non-compact Lipschitz theory base P1 cross C. And we can depict the base via a 2D toric ambient space, as I depicted here. And the next, we can decorate multiple additional rays into the base topologies, such that they introduce n copies of small E8 instantons in the E8 cross E8 vibration. And once you project the whole toric ambient space into another directions given by the other coordinates of the rays, this will gives you naturally the other vibrations. So in total, we have up to at most 3 choices of the vibrations coming from the toric setups we consider here. And as a warm-up, I depict a very easy T-dual partners that depicts in the toric geometries. Namely, on the E8 cross E8 side, we place n+1 tensor multiplies, but with trivial gauge algebra supposed on each of them. And they are T-dual trivial in the SO32 vibrations with non-trivial gauge algebra SPN. And of course, they have the matched data, as I mentioned earlier. And moving forward, we can consider more types of the generalized 60 distinction quiver constructed from the toric geometry. So one particular, we can decorate each toric rays by the copies of the E-thick gauge algebra, such that we obtain the following quiver. And once you include the m copies of the conformal matter vectors E6, E6, one will reach to the full quiver of the 60 distinction series. And the second vibrations, I still have some spaces here, I will depict it here. So these we can easily see that one can easily read the 60 distinction quiver from the curve configurations as I depicted in toric setups on the left-hand side. So I wish to emphasize briefly here that usually there is so-called fiber-based dualities that can be observed in many cases here, such that the base topologies of the T-dual theory will usually respect the singularity types that you are chasing in the dual series. But here there's some subtleties that it is kind of like a quotient-based topologies that I hope that my collaborator will collaborate more in the applications of the novel distinction series that's from the geometric concept I introduced here.
I have a question.
Sure.
How do you pick the example? Is there a notion of the simplest possible example?
You mean this example of E6, E6? E6, right?
Yeah, how do you pick your examples?
I just randomly pick because
random choice.
I think if I chose E8, maybe the space is limited. So in our work, we vary any types of the E-type singularity here. Namely, we consider any types of the E7, E6, E8 as the flavor group choices as well as the singularity choices. So here I just randomly pick.
I see. I'm looking for a notion of simplicity, something which will make one
maybe more
simpler
is to approaching the A-type, but the issue is the A-type and D-type are already can be exploited in the dual brain pictures that in the first part of our work. So I think it'd be nice to depict one type of the E-singularity setups in the work as here to emphasize the power of F-series geometry.
I see. Okay.
Thank you. Now I wish to talk more about the other geometry aspects in underlying the Calabi-Yau threefold, namely that we can utilize the underlying K3 geometries in the Calabi-Yau threefold to derive more T-dual families. Let's quickly review what happened in the 8D. That there is so-called stable geometry limits, which links the K3 in the F-series to the heterotic strings sitting on the torus of the heterotic. And in terms of the K3 lattice geometry terminology, the choices of the flavor FA, FB bundles is determined by the picker sublattice embedded in the homology lattice, which is given by the intersection form of the second cohomology group of the K3. And among these homology lattice, the most important sublattice is the so-called Neron-Sevilla lattice. That it is spanned by the divisors modular intersections forms of the divisors and modular rational equivalence. And moreover, the transcendental parts of the NS lattice gives you the possibilities of the complex structural deformations of the K3. And if we wish to study the infinite vibrations in K3 using the lattice techniques, this is nothing but to embed the hyperbolic lattice U into the Neron-Sevilla lattice, such that first parts informations of the vibration, namely the zero sections and the base, are contained in the hyperbolic lattice U, and the rest parts, the so-called frame lattice, will record information of the ADE type root lattice as well as the moduli group information. So that's just to say the non-abelian and abelian parts of the series is encoded naturally in the frame lattice. And let me just give a very straightforward case. Say we want to consider Y cross Y heterotic series, then we simply pick the decompositions of an NS lattice into these forms. And one naturally anticipates that if we consider multiple U embeddings into the NS lattice, we can obtain more effect vibrations. For instance, another embedding with the SO32 fiber and the other two moduli groups that will give you the spin 32 multi 2 series. This unifies the series naturally in the K3 lattice language. And we anticipate that using these techniques, we can obtain the more than the limit amount of the T-dual family given by the toric constructions I listed earlier, once we approach to the 60 series. So of course, once one moves to the 60 division series, we consider two fiber least elliptic K3 over a non-compact directions. This will render the nested vibration structures as I depicted here. And once one adds more non-trivial compact curve to the Calabi-Yau threefold, the K3 will degenerate in the origins of the C. See next slide for more informations. And such that all the 60 degrees of freedoms collapses in the generalized singularity of the origin. And once you perform the resolutions, it will give you naturally the full 60 illusion theory quiver. So one can feature the properties of the 60 illusion series and using the informations of the K3 vibration as well as its degeneration. So namely, once you move to the 60 Calabi-Yau threefold, the NS lattice of the K3 is where connects to the over lattice of polarization lattice of the vibrations. Namely, it will connect to, sorry, it should be the lambda S. I should use another notation apart from the K3 second homogeneous group lattice. Namely, it connects to the intersection form of the non-compact devices DI into the Calabi-Yau threefold and then restricts to the K3 surface. So that's how we naturally connect the information from the K3 to the overall Calabi-Yau threefold. And once you filter in the incidental lattice in the K3 fiber, it refers to the choices of the two embeddings that's relevant to the right connection choices at infinity. It gives you different various types of the favor groups types that you can obtain from the K3 fiber. So one no longer needs to study the embeddings of the MUI. One no longer needs to study the MUI directly, but we can transfer all those languages to the K3 fiber. And then at the end of the day, in our work, we will focus on an extremal K3 surface and identify that a T-dual families, which contain 6 components. So Paul will give more details about this T-hexylated family we found in the work. And here I want to emphasize more about the K3 degeneration. So in the literature, some certain types of K3 degeneration are described in terms of Kulikov models. There are 3 types of them. So the Kulikov models is just to describe the behaviors of the smooth K3 around the neighborhood origins of the base. So namely that once you move around the base C, the K3 might, over generic point of the base, see that the K3 remains smooth, but over certain points, the K3 could be splittable. And the intersection patterns of these splitting components determines the types of the Kulikov models. However, the Kulikov models described by Kulikov is very limited, means that they don't consider all possible intersection patterns of the splitting components, they don't consider multiple LSTs of the spanning components as well. So at the end of the day, to serve our purpose of the distinct theory studies in our current work, we wish to generalize the Kulikov models into a Kulikov-like ways to study more intricate fiber structure. So here is the depiction to give you some visualizations about how the Kulikov models looks like inside of the whole vibration structure. So I refer to my colleagues' talk later to tell you more details about these Kulikov degenerations. So at the end of the day, I wish that my talk regarding to the geometric dictionary between the 60 novel literature series and the F-series geometries gives you an idea about the geometric engineering technique we used here. And we managed to construct many types of literature theory, which proves various types, namely all types of the singularity, not just the simply list, but also non-simply list. And the T-duality were verified by the matching of the column branch and tensor branch data. And as an outlook of the whole triology work, I listed the three possible directions. Namely, one can turn towards to non-heterotic literature theory without neighborings in the system in the dual brane pictures. And one can also incorporate the possibilities of the twisted compactification, which comes from the multi-section structures of the modular groups. One can also relate to more general classifications of heterotic literature theory using the degenerate K3 surface. And this will study the unexplored reducible K3 fibrations occurs in the geometric literature theory we studied so far. So thank you.
All right, let's thank Muyang. Do we have some questions now? Immediate ones? If not, then I would say let's turn it over to Paul-Konstantin.
Sure, I'll stop sharing.
Good, good.
Wait, okay, stop.
Oh, I cannot start screen share. Because
Oh, you should be.
sharing. Now it should be possible. Okay. So let's see.
Very nice.
Very good.
Looks
Okay.
good.
Excellent.
Very good. So, well, we'll have the fourth part of the series, the second one for today, by Paul-Konstantin Oehlmann. The poly-ality of heterotic LSTs. Take it away.
Yeah, great. Thanks, thanks, Julius, and of course also thanks to all the organizers that we are able to tell you so many good things about heterotic little strings. And so I guess I have to. I'm the last speaker, and then you have to usually summarize everything that came before. And so I guess the topic a little bit of my talk is going to be well, quivers. So I'm going to use all the geometric data and all the information geometric introduction that Muyang gave to essentially give you a quick run through all the nice things that we found when we looked at the geometries of these heterotic little strings. And the message is a little bit, the message is this surprising poly-ality. So it's sort of this phenomenon when you start to look at these little strings, you start to find more and more facets or faces the longer you're looking into them. And well, I hope I could express this a little bit with this picture here. And there are going to be questions after the talk, how many faces you have seen. Very good. So these are supposed to be 10 Indian, damn it, no, I said it. Okay, these are X number of, of Indian presidents that are hiding here. Okay, but you still have to name them, and you still have to find them and tell me where they are. Okay, good.
Okay, thank you.
And as Muyang just said, so this work is sort of based on this part 1, 2, and 3 with Michaela and Muyang, and then we have this follow-up project which I don't know, I will just call part X, because I think probably part 4 is going to be reserved for Marco Fazzi and Zuvendu's work. But okay, let's start. Here we go. Okay, sorry. Here we go. Okay, so I think I would like to start with a small step back about heterotic little strings and say a little bit more from the field theory perspective, like from a little bit from my perspective, where in this space of 6-dimensional theories they are sitting, and why I personally come to like them so much. And the reason why I like them is that they are literally sitting in between supergravity theories and the 6D SCFTs. And the reason for that is, and that's actually a geometric fact, is as soon as you have a 6-dimensional supergravity theory with more or equal than one tensor multiplet, you are always going to be able to make a decoupling limit to get a heterotic little string theory. In the F-theory language, that means if the base of your vibration is a Hirzebruch surface or a blow-up thereof, you will always be able to make a decoupling limit and get a heterotic little string. So that's actually cool, because maybe heterotic little strings can also tell you a couple of things about supergravity theories. And then, of course, the next thing you can do is you can always decouple another tensor multiplet, and then you're going to get a 6-dimensional SCFT. When you just when you compare these theories, the main feature of the little string is also that, feature-wise, they also sit right in between SCFTs and gravity theories. So, for example, they do have a scale, like a characteristic scale, the little string scale, just like a gravity theory, which has the Planck mass, but a 6D SCFT does not, sort of by definition. And on the other hand, unlike gravity theories, a little string has global symmetries. No? The typical quantum gravity law is that you're always going to have gauged symmetries or broken symmetries, but here 60 little strings, they can have global symmetries, just like their SCFTs. And because of the typical scale that you have, you're going to have the feature that you can match global symmetries across dualities. And also 6D SCFTs do not have dualities or T-dualities. That's something which is usually reversed for theory that has a scale. And that's, of course, sort of the idea of this whole program, that with little string theories, we are now able to match global symmetries across dualities. And we, of course, going to use these the higher symmetries in our work. So this gives you roughly like a nice connection between these various different things, where the heterotic little string takes center stage. So we're going to have this nice connection between the two group symmetries and then the dualities that you can map them across, and then this very nice geometric picture of elliptic K3 vibrations that Muyang was talking about. So the general question for this sort of concluding talk is what are the general rules of these dualities, for this heterotic little string dualities, and what can we engineer? How do they generally look like? That's sort of the topic of this talk. So that's roughly my outline. I will pick up really quick where Muyang just left. So I will remind you a little bit in a very cartoonish way what the geometry of these little strings are, and how the typical heterotic little string dualities would look like. And then I will tell you a lot of things about exotic little strings and the poly-ality that you have before I will conclude. Good. So let's start. So the first thing for this heterotic little strings is this feature that in the F-theory geometry, which is just elliptic Calabi-Yau 3 over a non-compact base, the main feature is that that in the non-compact base B2, you're going to have this unique curve sigma ls, which has a vanishing self-intersection and is either of genus 0 or of genus 1. And depending on which of the two you have, it's either a heterotic little string or it's a type 2 little string. And of course, we're gonna focus today on the heterotic roots. Good. Actually, from this extremely simple observation that you just have these very general bases and these general geometries, you immediately find that whenever you have, say, a compact base with a curve of vanishing self-intersection, there is a so-called Kolar criterion that immediately tells you you're going to have a K3 fibration. So from just this very simple fact that you have a self-intersection 0 curve of genus 0, you can immediately deduce, okay, there's a K3 fibration in your geometry. That's pretty cool. But it's maybe also not so surprising because, because of the heterotic F theory duality, which makes use of the fact that there's a K3 fibration, it's maybe sort of even expected. But the point of this geometric thing is, as Muyang was saying, is that your threefold geometry has this nested fibration structure. So you have a Calabi-Yau 3, which is K3 fibered, and the K3 is torus fibered. And that's going to be the F theory torus. And then you can, as Muyang just said, very nicely sort of split up the properties of your little string. So the flavor group is typically are non-compact divisors that sit inside the K3. So the K3 is sort of the flavor K3. That's what it does, gives you the flavor group or the geometric flavor group. And the dynamical degrees of freedom are located at the point of this K3 fibration where the K3 fiber becomes degenerate. And that gives you this nice geometric picture that you just saw also in this in the talk by Muyang, that the geometry of your fibration is roughly this K3 fibration, which is self-elliptic over this curve sigma ls, which is the little string curve. Then there's maybe a couple of resolved fibers here. This is an SO8 here. What is this? That looks like an E6. And so that is just a part of the flavor group. And then at the origin of this K3 fibration over C, the whole collection becomes reducible, and you get these nice quivers that we have seen before. And because here are all the compact divisors that give you the dynamical degrees of freedom. And the nice thing is that this whole picture gives you a very nice geometric or mathematical analogy to these generalized Kulikov degenerations. So apart from these fiber guys here in between, this is precisely how in mathematics a so-called Kulikov degeneration looks like. So it's actually very suggestive from the math perspective that the geometry of these K3 degenerations is basic, or studying that is essentially the same thing as studying little string theories. Okay, so that's the rough picture. And what are the lessons that we are getting from that? So the first lesson is, that's just what I said before, the K3, or better the Néron-Severi lattice, as Muyang was saying, gives you the geometric flavor group. And now we can exploit all these nice mathematical results by not only Shimada and Miranda Persson, but also many, many others, that first of all tell you there's only a finite amount of K3 polarizations. So that's already pretty cool. That's roughly the same thing as there's only a finite amount of compact Calabi-Yau threefolds, but or elliptic threefolds. But the point of this mathematical fact is that we have only a finite amount of flavor groups. And that's for the heterotic little strings. And that's super cool. It just comes out of the math. The second fact that comes out is that the rank of these K3s is actually bounded, because the Euler number is fixed. And the rank of this NS lattice can never exceed 20. And that immediately tells you, once you take the class of fiber and base, the rank of the flavor group can never be greater than 18. Booms. That's the next mathematical fact that you immediately get for free once you realize that there's a K3 fibration. But then we can, of course, do many, many more things, and that's what we also do in a second. We can extract many properties from this K3, namely the reducible fibers that we have seen before, but you can also reduce or deduce the model Weil group, which gives you the abelian flavor symmetries. That's usually a pain. And you can also extract essentially the non-simply connectedness of the flavor group if your model Weil group is finite. So then you can immediately deduce that that you actually have for your flavor group such a quotient structure, and that's going to affect all the quivers as well. Something I will comment on at the end is that we also going to be able to deduce all the different elliptic fibration structures just from this K3 data.
I have a question.
Please.
So there used to be statements which mainly centered around single gauge groups, that U1 symmetries cannot appear as flavor symmetries, but this probably is not correct. What's the more precise statement about abelian flavor symmetries?
I think the result by these gentlemen here in their series of works is that, well, they do appear, they are there, they're hard to detect. So essentially you have to just propose them, see, give a general charge assignment, check if they are free of ABJ anomalies, and then you're expected to have them in a 60 theory.
I see. And is there any estimate of how many for a given geometry?
I would say always less or equal than 18. But
I see.
But I don't know if that makes you happy, if it's too much or too little.
Well, at least it's a bound. You see, it's good. It's a good start.
Indeed. I mean, it's a known fact that K3s, elliptic K3s, cannot have a model Weyl group which is greater than 18. I mean, basically, I mean, I think it actually has been even constructed. I don't know what the quiver to that would look like, because we're just talking about flavor. It doesn't mean that the quiver to that exists, but I would expect, that's what I would expect. Yeah.
I see. Okay.
Good.
Thank you. Yeah.
Sure. Yeah, good. Let's continue. So now what I'm going to do next is I will sort of go through the different lessons that we have on examples. So there's not going to be any formulas, just quivers, and in 6-dimensional quivers. So but they are sort of exemplary for the more general lesson. So the first lesson, that's essentially what Muyang has told you also, is the fiber space duality. So now I'm choosing not to switch on any flavor group here and just keep the E8s. And I'm starting from the E8 picture also in my heterotic little string, this Java-Witten picture. And I have this number of n NS5 branes here, then you get these curves, and I'm decorating then with some gauge singularity G here, which sort of sits transversely in the space. So I just chose here to put an E7, and that's of course like only a partial tensor branch. You have to think of putting the conformal matter in between all these different guys. So then if you dualize, if you just look into the geometry, you see what you get is you get your SO32 dual quiver. And what you find is it's some sort of orthosymplectic quiver of SP and SO groups, and it has the exact shape of the affine E7 or the affine G singularity. And that's a very general message that you have. You have it for E8 and for D-type singularities, and the only exceptions here are if you take as a singularity here an SUK or an E6 group, because then what you're going to get in the dual base is just the folded version, if you want. You get an SPK half and an F4 affine quivers, respectively. But this whole picture, how the dual base geometry is going to look like, is fairly independent of the flavor deformation. Now, even if I break here my E8s to something smaller in using my K3 rotation, I will also break the flavor here, but the shape of this quiver for large enough n is unaffected. So that's a general lesson. Very good. So, but that's fairly standard. That's something that Aspinwall and Morrison have already figured out, and I should have cited them here. So now comes the first thing that we noticed when we went into the details of these geometries. Let's, for example, do a discrete holonomy breaking, meaning I break the E8 into E7 times SU2 mod Z2. So this is now how my quiver upstairs would look like. Okay. Now think again about the various conformal matters in between. Then you look into your T-dual and you don't find big surprises. Like I said, the T-dual geometry still has this E7 type of shape and a broken flavor group. Nothing too exciting, but the exciting thing now was that from the toric geometry actually found a third T-dual. And what we found was that the shape of the new quiver, and this is actually something you can really see when you track the fibril divisors through the T-duality, you find that the shape of your of the new base is actually more like an F4 singularity that you would expect from an E6 singularity. Actually, if you look a little bit closer, you can literally see that these base divisors here that you had in your E7 are sort of mapped on top of each other through the duality, and they become this. So it actually looks more like an E6 too from the shape. Yeah, I mean, I should of course say this is still the intersection form of these quivers is still symmetric. It's not like a non-simply laced type of base, but the way how the things are mapped on top of each other is really as if you would have a twisted affine folding for the base, and that's a fairly generic feature that you find for your third duals in these models. So another nice example we have that we can fairly well control is when you go to the case where you actually start off in the E88 picture for 0 NS5 branes. So you just take all these guys here away, and then you literally would get such a 0 curve here. Yeah. Again, think about putting in the conformal meta resolutions in between. Actually, this 0 curve by itself, and then probing by this flavor and E7 singularity here is literally the heterotic string. No, the string that wraps that 0 curve, that is literally the heterotic string, and probing it with such a singularity is really what you would get is really the fractionalization of the heterotic string itself once you probe the singularity. And from this whole geometric approach that we're having, it's setting up these models and looking in the dualities of them is just as hard as the generic N case. So it's really fairly simple. Also remember the way how Marco has seen the approach of these models is that you can always say start from this Hojava-Witten picture here, and you can view it as the fusion of two Orbi instanton theories, or let's say the other way around. You can always cut it in the middle here, and you get two Orbi instanton theories. This is not possible when the N is just too low. Yeah, I cannot cut the 0 curve anymore. What can I do? So these are sort of exceptionally simple models. So maybe this is something that is particularly simple for you, Hanan. But the surprise then is we can of course also go through the whole geometric setup. And these models typically come with an enhanced flavor group here. You would get a couple of more fundamentals. Yeah, note again, this is before I'm doing the tensor branch. And in the dual quiver, what I get is not quite an E7 shape, but a couple of nodes are missing. So here and there, these nodes are just missing for these specific values. And you also find the same enhanced flavor group here. Yeah, you see the flavor group here is already getting higher than rank 16 of the E88. You get this additional piece here. I suppose this should be like an O2 flavor group, and here you find an SP1 additional flavor group for the SO8. So this is a generic thing that you find for very little n. You find that the duality of this, or this fiber-based duality, is not quite perfect. It starts to sort of miss a couple of nodes in the dual quiver. The second thing you can do is actually not precisely fuse models together, but you can, for example, here, I could just fuse these two rank 1 Orbi instanton, or these two conformal matter theories. I can fuse them together on the E8, but I don't want to do so. I want to fuse them in the middle here with the F4. And what I'm getting is a model like this. Yeah. So this is some sort of partial or incomplete fusion, where I've used these two theories sort of in the middle, and the conformal matter, so to speak, starts to overlap. No, it starts to go into each other. No, this is something I can easily do geometrically as well, and I can produce a dual one, and that's how they look like. No, so and note also that typically these models come with enhanced flavor groups. But of course, I have a lot of geometric freedom here that I can do. I can do the same thing for the G2 here and there. And I fuse along the G2 node, then I get something like this here, and I can also dualize this guy, and I become this. I get these very short but exotic sort of quivers. So all these things I can do, and we explore them in the various papers. So one thing which is also very nice, and that also works pretty well, is to consider twisted T-dualities. So what does it mean? So I can of course, I mean, all these T-duality, as Muyang said, have to do with the fact that I have multiple fibrations in my geometry, and they are related to M theory, which is just a circular fibration of F theory. But now, if I have certain automorphisms, I can twist by them, and I get a twisted algebra in 5D. And what has been well widely looked at in this paper by the Wafa group and by the Kias group, and also by Bardwaj, I think at the end of last year, is that the geometry behind those is actually a genus 1 fibration, and you can precisely have these twisted groups. And in some finally upcoming work with Lara and James, we also have one example where we have a decompactification limit of a supergravity theory, where you have two twisted T-dual little string theories, and one of them is actually twisted because it's a genus 1 fibration. And you can actually also show that in these models, the number of two groups, or the two group data and the Coulomb branch data all matches across. And that's actually extremely powerful, because recall that the two group structure really depends on the dual Coxeter number of your gauge algebra, and that is very sensitive if it's twisted or untwisted. For example, F41 has a dual Coxeter number of 9, and E62, which also has an F4 subgroup, but is its Langlands dual, has a dual Coxeter number of 12. So these are really very different quivers, and it's highly non-trivial that the two group data of these two guys matches. Very good. Then the final thing I wanted to talk about is the attractive flavor groups and the poly-ality really of the little strings. So remember again that we can have these very large maximal flavor groups from the K3, and when the K3 has such a maximal flavor group, meaning its Picard lattice is maximal, those K3s have a name, and they're called attractive K3s. So those guys are special because really the whole second cohomology is completely in the Kähler sector, if you want. Okay, very good. So these K3s that you have in our little string setup, they would sort of relate to little strings with a maximal flavor group. The cool thing about these guys is that mathematicians have actually classified many features of such K3s. It was actually like a big sports. And they have, for example, classified all the elliptic fibration that this single K3 can have and what the fiber structure is. And the nice thing is that all these geometric tools that we have just talked about of the toric geometry, we don't need it. It's completely unnecessary to understand all these different fibrations. We can just do it in terms of lattice data. So we can start with a K3 with its transcendental lattice. From that, we can actually, using this Kinesa-Nishiyama method, we can obtain the NS lattice and all its splittings into the hyperbolic lattice and the frame lattice. So that is nothing but a classification of all elliptic fibrations that this single K3 can have. And like I said, the powerful point about this is you can do it in terms of lattice data. You don't have to do a resolution or anything. It's just lattice data. That's extremely nice. And what you actually find is, and this is just like an example that hopefully is a bit, well, it's a bit bigger than the T-hexality that Michele showed last week. We actually have one very concrete example where we have it. Okay, now I have to check a T-tridecality. So these are 13 T-dual little strings. And what I've pictured here is just the flavor group. Yeah? So you find, of course, your typical, sort of typical guys that you know. Here you have the E88, but you have this enhanced SU2 squared, and you have the SO32 also with the same SO2 squared flavor group. But of course, this whole picture is way more enhanced and goes broadly beyond this Ojava, Witten, and Tendi duality of a gauge group, of the heterotic gauge groups. So here, for example, just if you want to look at here, you find an SO12 to the cube. So for me, it's not extremely evident sort of from the heterotic picture how you should see it. No, it's like one SO12 comes from one E8, the other SO12 comes from the other, and then you have a little bit like a mixing happening with other isomorphisms. So that's sort of funny. Or the same thing here, you have an SO36 flavor group, which is also very, very large. And it's sort of like a non-geometric enhancement of the 10D heterotic SO32 group. And actually, if you look a little bit closer into this, you will realize that these dualities that you have here are really inherited from 8-dimensional supergravity theories. Yeah. So very good. So we have this, and from this whole data, you can actually also start to construct now quivers. Like the full little string, not just the flavor group. And you can, and that's the nice thing, but I will not go into the technical details. You can do it just from the K3 lattice data. You don't need any resolution. You don't need anything. You can really just get all these dualities, all the flavor groups, all the data just from the data of the K3 alone. And of course, by construction, the number of the rank of the flavor group, Coulomb branch, and the two groups, they're all matched for all these quivers. So here I was a bit lazy. I just put in the first 5 of the 13 different ones. Like a big takeaway for all these models is, of course, that they are sort of isolated. So they don't exist in families, but they really are just these isolated different models, and you don't have such huge dualities for like any number of NS5 branes. Okay, I think this already brings me to my conclusion. So as I hopefully convinced everyone, is that the network of heterotic little strings is very rich. You can find a lot of nice things, and the powerful tool that we are really using here is this interplay between the geometry and the matching of the higher symmetry to really chart out this whole network of T-dual theories. While doing so, we find many nice new features, like this more generalized fiber-based duality, where you can have these sort of twisted affine folding on the base quivers, and you find these fractionalizations of the pure heterotic string, these partial fusions with non-simply laced algebras, and you can of course also do twisted algebras. If you don't take anything from this talk, this is the main thing. We find, and that was a surprising thing, that the T-duality is actually not a duality. It's a poly-ality. So you find many, many dual models, in particular when the flavor group is large. And we can construct them using lattice techniques. And what we, for example, find is easily with the toric methods, we find the T-triality, we have a T-hexality. I just showed you the T-tridecalities. And in fact, mathematicians have shown us that there's also examples with, okay, T pentaconta aka etriality. So that's a model with 53 duals. That's pretty nuts. So those dualities do exist, and mathematicians have classified them. So an outlook for which sort of things we can do in the future is, of course, we are currently finishing and charting the toric network and see what other nice, interesting things we have missed there. Obviously, now that also the twisted T-dualities become accessible, we also would like to look at those. And of course, one can also fairly easily do the same sort of program for the other type of little strings, namely the type 2 little strings, which we are currently doing. But I can already say that the structure there is much stronger constrained and not as rich as in the heterotic case. And then, of course, there's many other questions like looking at elliptic genera, going to lower dimensions, and actually seeing how the little string story can potentially be coupled to gravity again, and potentially even tell us something about the swampland. But yeah, I think I'm going to finish with that. Thanks.
All right, let's thank Paul-Konstantin. Do we have questions? Did anyone forget how many faces there are and wants to?
such a flaw.
So this
Yeah.
if you maybe go back
Yeah.
just one or two slides. Okay,
Mhm.
one more.
Yeah.
Yeah,
yeah.
so this penta, cotta, akka,
Oh,
duality.
that one here.
Yeah.
Yeah.
Do you have examples of this, or do you just know that this should be there and you have...
Good. Yeah, we have not looked at it yet in detail. We know from the mathematicians that there exists a K3 with 53 vibrations, different or inequivalent vibrations. Well, actually, it can, I should say that it could be that that there's a different, like an inequivalent vibration, but it has the same fibers. That can happen. That they are sort of, and then that would sort of result in like self-dual little strings. That can happen. But we have not looked at them yet in detail.
And do you
Yeah.
have examples of self-dual little strings?
Yeah, we do. Usually they happen when you have SO groups as flavors. Then, like, I don't know, I think we have one example, which is SO16, SO16, which
It's like a...
I mean,
okay, go on.
yeah, indeed. So what really happens is, yeah, you get well, you get just the same quiver when you go to the other phase, but it's of course it's still non-trivial, because you have to sort of rearrange the Wilson lines and the Coulomb branch data to get to the other quiver. They are not just on phase the same. You have to move in them. It's like you go to a different point in the Coulomb branch moduli space, and then you find the same. And so in that sense, it's still non-trivial. Yeah.
Very nice.
Yeah. So yeah, that was really the biggest surprise, that this network of dualities is so rich. Yeah.
Who are these mathematicians that have done this classification?
Oh yeah, I mean, this is like people like actually, I think well, I think there's a lot of nice reference in the Brown, Vatari and Kimura. They started to do some of them, and or we did some of them, and I think there's a lot of sort of scattered math work on that. I think I know of one, but I just forgot the authors right now. But there's like a couple of them that are bigger. But I think, as Andreas used to say, at a certain time, it was like a big sports in math to do those sort of things and find the K3 and all the vibrations, and because it's sort of a cute problem. But it's a bit scattered, and I think I'm not sure if there's like one paper that has them all. I think it's actually also not like completely solved yet to like do it for all of them. No? Yeah.
Okay, thank you. Do we have more questions?
More questions, more quivers.
Well, I guess we have some exciting stuff to look forward to, some more analyses. And let's thank Paul, and let's thank everyone involved in this. Very nice. And we can go off the record.